In the next talk, Sylvia is going to talk about a framework for network function virtualization.
Thank you. So the work I'll be talking about was with collaborators from Berkeley, Intel, and the University of Pisa. And I particularly wanted to call out Shoumik, Palkar, and Chang, who were the lead students on this work. Shoumik did the work as an undergraduate at Berkeley. He's now at MIT. And Chang is one of our PhD students. And the motivation for the system E2 that I'll be describing comes in large part from recent developments in the networking industry. And so I wanted to start by just elaborating on that context so you know where this is coming from. In networking, when we talk about what the inside of a network looks like, we often have a picture that looks a little bit like this, where I have switches and routers interconnected by links, and the primary job of these devices is to forward a packet along. In reality, however, this picture doesn't look half as simple and pretty. In addition to these switches and routers, we have a number of specialized devices that do a large set of additional functions. So things like firewalls, proxies, intrusion detection systems, or WAN optimizers that do protocol-specific optimizations. And so we call these middle boxes. And over the years, we've seen more and more middle boxes being introduced in the network. In fact, a recent measurement study showed that in many networks, you have as many middle boxes as you have switches and routers. And so in today's networks, middle boxes are this crucially important part of how we build networks. However, at the same time, they bring with them a fair amount of pain. For one, these are boxes that are dedicated, so I cannot just shift unused resources from the one to the other. They are fixed function with very little programmability, so operators have very little by way of options in terms of adding new features or modifying existing features. They use specialized hardware and software, and perhaps worst of all, each box comes with its completely own custom management API. So this is true across middle boxes, and it's true across vendors of a given middle box. And so the management costs associated with middle boxes have been incredibly high over the last few years. And in recent years, there's been a growing recognition. Middle boxes have kind of crept up on us, but there's been a growing recognition about the problems they bring with them and an unhappiness with these problems. At the same time, from the systems community, we've seen much improved packet processing performance coming out of modern multi-core systems. And so over the years, we've seen an emerging proposal for a different way of building middle boxes, which is simply, rather than build middle box functions as dedicated boxes, why don't we just write them as software applications and run them on commodity off-the-shelf servers? The benefits, or why would you want to do this, are themes that are very familiar to us in the systems literature. It's the cost benefits of commodity solutions, the efficiency of using shared infrastructure, and the easier evolution and deployment that comes with software-based solutions. So industries really, in recent years, picked up on this approach. In 2013, a group of network carriers got together, and under the banner of ETSI, which is the European Telecom Standardization Institute, in standardization something, started this industry-wide effort to realize this move to software-based middle boxes. They call this network function virtualization, or NFV, and use the term network function to refer to these software-based middle boxes. And so I'm going to be using network function interchangeably with middle box to refer to a software-based middle box function. So the momentum in just less than 2 years, NFV has gained tremendous momentum in industry. There are now over 300 companies that are part of this effort, and it's really been dominating the industry press around the networking industry. So while this momentum is great and it's very encouraging, a closer look under the hood, however, is a less pretty picture. If we look at what's coming out as NFV products from vendors, they tend to be a 1:1 replacement of monolithic hardware with monolithic software. So this is already progress because we are getting software instead of hardware. But a number of the issues with middle boxes remain. So if you're a network function developer, every development or every network function is still designing from scratch its own idiosyncratic way of dealing with common issues like fault tolerance, dynamic scaling, and so on. And you still have these custom per app management APIs and no end-to-end architecture by which you tie these pieces together. So for operators, the management costs haven't really gotten any better. For developers, it's not clear that their development has gotten either easier or faster. So given this, the origin of E2 is really looking at this state of NFV and contrasting it to how we build modern data analytics systems, where in these systems we have systems like Hadoop and Spark that are in part a programming model, but also importantly a runtime framework. by which I mean that the framework coordinates the end-to-end execution of a job. It understands how the constituent tasks should be composed to form one overall job. And the framework also takes care of routine functions for developers. So if I'm writing a job in Spark, I get to focus on how I want my data processed. I don't have to worry about exactly how many tasks I launch, where do I run them, when do I kill and restart a task elsewhere, and so on. And so you can see where I'm going with this. Taking inspiration from this, E2 aims to be a framework for NFV. So the role that E2 would play is mirroring the data analytics systems, would be end-to-end management of individual network functions, and to provide general solutions to common tasks. The benefits, again, if we could realize this, simpler development for NF developers, and from the point of view of an operator, it both automates and consolidates their management tasks. So the questions that E2 addresses more concretely to achieve this is two questions. The first is, how do we express NFV jobs? So today we have in networking no such abstractions. Our abstractions are pretty low level. They're per box or per middle box level. Instead, we want to start with a higher layer abstraction that allows an operator to capture their overall requirements, the end-to-end requirements of how they want their traffic processed. And so for this, we introduce an abstraction that we call policy pipelets. And then the second question is, how do we execute these pipelets? Because these pipelets are a logical declarative statement of the operator's goals. The framework needs to execute them. We identify 4 functions that any framework should support in order to execute pipelets. These are sizing, how many network NF instances should the framework be launching, placement, where should it place them, composition, which is how do you make sure traffic is routed correctly between these NFs, and finally dynamic scaling, which is revisiting all the decisions made, the first 3 decisions made as your load goes up and down. And so E2's contribution is really in answering these 2 questions in terms of both the algorithms and the supporting system architecture for the system. So the traffic processing context in which E2 operates introduces certain challenges. Networking is always pushed for performance. In particular, we'd be targeting performance that's in the tens or hundreds of millions of packets per second per server. And latency for a given packet should be in the order of 10 or 100 microseconds going through a server. And so for the framework, this both means that it should not get in the way of performance, but ideally that it can actually help us in achieving these pretty difficult performance goals. In addition, most network functions are stateful. They maintain things like NAT address port mappings or reconstructed TCP session state information and so on. And we have strict requirements on the affinity between traffic and state. So I need to make sure that I send a packet to the particular NF instance, whether it's a VM or a container, that holds the state that's associated with processing that packet. And this is the framework's job again. So a quick outline of the talk going forward. I'm going to describe pipelets, which is how we express NFV jobs, and then how we execute these pipelets, and then present a few initial results. So in terms of pipelets, what we wanted as a high-level abstraction was quite simply an API that would allow operators to express how their traffic should be processed. So this would go something like this, for example, where an operator would say that for all traffic coming from a customer port, I would like it to be processed by an intrusion detection system. If the IDS deems the traffic unsafe, I'm going to send it to a logger. If it's port 80 traffic, I'm going to send it to a web cache, unless it's YouTube traffic, in which case I'm going to send it through some kind of parental control system. And all traffic has to go through some kind of traffic shaping function before it leaves my network. So I'd like to call attention in particular to the kinds of conditions we have on edges. We have things like TCP port 80. This is a classic network filter. I take a packet, look at its header, and I know what to do with the packet. But we also have things like URLs, which you can't really see by just looking at one packet. Instead, you have to look across packets, reconstruct the TCP byte stream, and then you know what to do with the packets. And then we have things like, is traffic unsafe? There's no amount of staring at a packet that will tell me that. This is semantic information associated with a packet that only the applications know. And so this is the kind of expressivity that we offer in E2. I want to point out that, 1, this is end-to-end. It crosses multiple network functions. 2, it's logical. We're not actually saying how any of this is going to be implemented. And 3 is it's general. So from a networking context, this is going past the traditional header-based rules to something that captures as well traffic semantic information. And so more formally, we define a pipelet as a statement that maps a traffic class to a policy DAG, so it's a directed acyclic graph. The traffic classes we support right now are defined on packet headers and physical ports in a cluster. And the DAG is a graph where the nodes are network functions, and the edges define the conditions under which traffic is going to flow along a particular edge. And we do this through filters that are just general attribute value pairs. And in addition, optionally, we have an estimate of the traffic load that you can associate with an edge. We'll use this in making better placement decisions. So just again to recap, this is an explicit statement of policy where today network operators implement policy implicitly by sticking their middle box in a convenient place in the physical topology. Here we're starting top down. It's end-to-end and it's declarative in that I've not told you how to do any of this. For example, how do I know if traffic is safe or not? So that gets us to the second piece, which is how do we actually execute these pipelets? Let me start with just the context, the system infrastructure we assume. We have a cluster that's pretty much a standard cluster. You have switch fabric. In the case of our prototype, it's actually a single switch that interconnects servers. Some of these ports are what we treat as external ports. This is where traffic comes in and out from the rest of the network or the world. And then we have the rest are internal ports. Within each server, we assume we have a bunch of network functions. We try as hard as possible to treat these as black boxes. And they run on top of a software switch. And within the switch fabric, the component that's of relevance to us is the flow table, which holds a set of match action rules which tell us how to steer packets through the switch. So for example, if you have this destination IP address, go out port number 39, for example. We have a manager, E2 manager, which plays a little bit, you can think of it as a scheduler in a MapReduce system. It takes as its input this high-level policy pipelet and configures all components of the system to execute that pipelet. This is a very standard system architecture. Actually, you'd see it in almost any cluster. What's different is, one, the internal logic that's inside the E2 manager, which I'll describe shortly. And the second is architecture for a software switch. So let me elaborate on that right now. If you look at data centers, the de facto virtual or software switch that people use is based on OVS, the Open Virtual Switch. And it has an architecture that looks a little bit like this, where you have physical ports that go from the NIC to the software switch, virtual ports by which applications connect to the software switch. And then internally, the software switch, you can think of it as this flow table, which has, again, simple match action rules. So really, a virtual switch is pretty much no different from a hardware switch in terms of the functionality it supports. But for E2, the software switch, the role of the software switch is critical because this is the only place where the framework gets to interject control over the traffic, because the network functions themselves will come from third-party vendors. And for many of the things we wanted to do, we needed to be able to put more complex processing inline, and we needed more flexibility. So the OVS, or the canonical software switch architecture, really didn't work for us. So what we use instead is a different software switch architecture. It's based on a system called SoftNIC, which is another project at Berkeley. The code is available publicly on request. But it's a standalone project, so let me only highlight the pieces that are relevant to E2. The main distinction from existing software switches is the internal architecture, where in SoftNIC, you can compose a data flow of little processing elements between any physical and virtual switches. Some of these elements might be switching, but they can also be general processing. For those of you familiar with MIT's CLIC router system, it's very much inspired by CLIC. So in E2, we take SoftNIC, and we make a few additions. The first is in the abstractions of a virtual port. We support the legacy virtual port abstraction, but we also support something called byte stream ports. What byte stream ports allow you to do is it allows two network functions to directly exchange the TCP byte stream between them. This is useful because one of the first things many network functions will do is to take a set of packets, strip out headers, reconstruct the packet byte stream, and then they'll process that byte stream, repacketize it, and send it back out. There's no fundamental reason why we should be exchanging packets. We can directly exchange byte streams. The other abstraction we add is this notion of metadata. So in a vPort now, when I send out a packet, I can also have metadata associated with that packet. And again, in many packet or traffic processing applications, internally they have some notion of metadata. What we're doing is extending the abstraction so you can expose that across applications. And this is very useful for communicating semantic information about packets. And then we have a richer API reflecting the fact that we have a richer internal architecture, so you can add and remove modules. And then we introduce a number of modules that implement the functions I'll be talking about shortly. So with this architecture, how do we actually execute pipelets? So E2 will operate on 3 inputs. The first is the policy pipelets I described. The second is what we call a network function or an NF description. We imagine this as being NF-specific configuration information that is handed to you by the vendor or the developer of the network function. The most important piece of information in this description is which attributes a network function exports and how. So this is a binding between attribute values and a particular method. And the methods we support right now are twofold. There's virtual ports, either packet or byte stream based, and metadata. So now, for example, an NF might say something like all safe traffic comes out over virtual port number 4, or URLs are exposed as a second metadata field associated with packets and so on. We also need information about the affinity requirements for the application. Does it process per flow state, per prefix state, per port state, for example? And finally, an optional performance information. For us, we use the per core throughput of the network function. And then the final input is a description of the hardware resources available. How many cores do you have per server? What's the I/O capacity per server? And so on. So with these 3 inputs, what E2 is going to do, the first step is what we call sizing. So it takes all the individual pipelets, combines them into one big policy graph, and there's certain sort of soundness checks you have to do when you do this combination. And then we convert this policy graph to what we call an instance graph. So remember, in the policy graph, a node is a purely logical representation of a network function. In the instance graph, every node represents one instance of this is actual running code for the network function. And this we can do from the information we have from the inputs. You have to be a little careful in drawing the edges to maintain affinity, but I'm not going to go into that. The next step is placement, where we take the instance graph and we decide which cores in the cluster each of these instances is actually allocated to. Our goal here is to minimize traffic going through the switch. And you can model this as a graph partitioning problem, which is known to be NP-hard. So E2 uses an algorithm that's a slightly modified form of the Kernighan-Lin, the classic heuristic for graph partitioning. So if in our instance graph we have n nodes, this gives us an initial placement that's order n squared log n to compute the placement. And we also have an incremental version of the algorithm where if I'm given a placement and I add a few nodes, I can compute the placement for the new nodes in order n time. Our final step is composition. So now we know where these network function instances are running in the cluster. We have to make sure we direct traffic between the network functions in accordance with the conditions that the pipelet gave us. So this comes down to appropriately configuring the hardware and the software switches in the cluster. And appropriately here means answering 3 questions. The first is you have to identify, or E2 has to identify what traffic should be sent to an NF. This is a matter of reconciling the attributes that were on the edges with the methods that the network function exposes. And so E2, the framework, will automatically select and configure whether it's using virtual ports or metadata or header-based matching. We then look at how traffic is sent, and this comes down to choosing between packet versus byte stream reports. And finally, which particular network function instance you should send traffic to. And the challenge here is in maintaining affinity. So I had a whole bunch of traffic going to, let's say, one instance of an IDS. I now have 2 instances of the IDS, and I want to split my traffic across them. But I have to do so in a way that maintains the affinity between the traffic and the state that's needed to act on that traffic. And in recent years, there have been a few papers at NSTI and SIGCOMM that address this problem. And they all achieve optimal load balancing. But they do this by relying on state migration. And this creates a very hard problem because you have to perfectly synchronize state migration with traffic migration. And so you end up with these pretty complicated solutions where people are, for example, running 2-phase commit protocols across the distributed switches in the network. We wanted something that was simpler and that would also work with legacy network functions that don't support state migration. And so we have an algorithm we call migration avoidance, which does not require state migration. And what it sacrifices is the optimality of load balancing. But we show that for certain flow size distributions, in particular, if you have a large enough number of short flows, which is the norm in networking, then you will eventually converge to the optimal load balancing. And I'm not going to go into the details. It's in the paper for those of you who are interested. And so going back to the operation, we have these 3 key components. The last bit is, as I said, dealing with variations in the input load. And simply, as our load changes, we update the instance graph, then we run an incremental version of the placement algorithm, and we reconfigure traffic using our migration avoidance algorithm. And that's really the key overall operation of E2. So let me just close with a few performance results of E2. The first question one might ask is, what overheads does E2 add? And on the data plane, our main overheads are going to come from the abstractions we've added to the software switch. So we measure this using micro benchmarks, where we have 2 network functions, each running on 1 core each in a single server. And traffic between them flows through our software switch, which also runs on its own dedicated core in the server. Our baseline here is the latency and throughput that Softnik out of the box would support. And here, this is just the 2 network functions sending traffic over 2 virtual ports. And we can see that the absolute performance here is pretty high. We can do about 15 million packets per second between the 2 cores. So this is nothing that E2 brought to the table. This is just what Softnik would give us. We look at the throughput, the impact, as you start doing header matching. We see a drop of about 16%. And when you add metadata matching, because we're adding a new field, you have an additional drop of about 6%. So bottom line, metadata does not come for free. It's a non-trivial throughput drop relative to just having virtual ports. But you cannot do everything with virtual ports. And so relative to the conventional approach of doing header matching, metadata actually adds very little additional overhead. So to switch to actually do these rich abstractions actually help performance, because that was our intuition in adding things like metadata and byte stream ports. Again, I'm going to go back to the micro benchmarks, and again, the metadata field. And here what we've done is we take an HTTP logger, and we modify it to export the URL using metadata. And then we filter traffic between network functions based on this metadata. As a point of comparison, we take a network function, a legacy network function that didn't have metadata. Our only option there would have been to insert a URL filter, extractor, and filter inside Softnik. For both these cases, we measure the cycles per gigabit of traffic. And what we see is that having metadata in this field can reduce your CPU consumption per packet by about 41%. So this is where having these richer abstractions actually helps performance. To look at the other abstraction we introduced of byte stream network functions, byte stream virtual ports. What we do here is we take 3 network functions that all act on the TCP byte stream. So this is an IDS which looks through the byte stream for a signature, another one that looks for the URL to do URL filtering, and the redundancy eliminator does some kind of ribbon fingerprinting to eliminate redundancy in traffic patterns. In the first case, we connect all these network functions with packet-based virtual ports. And so in that case, every network function is redoing TCP reconstruction on its own. And in the second case, we introduce a new network function whose sole job is to extract the TCP byte stream, and then we connect the network functions with a byte stream vport. As before, we measure the cycles per gigabit of traffic in both cases, and we see that using byte stream, even taking into account the overhead of the new network function, we still see about a 25% reduction in the CPU cycles per packet. The final result I was going to show you is E2, the end-to-end operation of E2, the system as a whole. We take a very simple pipeline of 4 network functions, and we run this on a cluster that had 68 cores in total. And what we're doing here is varying the input traffic load, which I'm showing you on the traffic load is on the y-axis and time on the x-axis. The blue line here is the input traffic load to the system. And we measure the resultant switch bandwidth we're consuming. The input traffic load is the optimal. That's the lower bound on how much of your switch bandwidth you could consume. We're about 16% higher, which seems fine considering that we're doing splitting and merging over the course of this experiment. We were also curious about how many the CPU consumption during as the system runs. So I'm plotting the number of cores here on the right-hand side y-axis. And what I'm showing you first is the optimal CPU consumption. We calculate this by saying for an input load, how many cores would the application have taken to process this input load. We sum that across all the applications. So this is optimal in the sense that it completely takes out of the picture any overhead unrelated to the application processing. We then look at our measured CPU utilization, and as you can see, it's quite a bit, depending on the time, it's a little bit higher, but it actually tracks the overall input load. And the higher overheads are to be expected. Part of it comes from our cores that we use for Softnik. We dedicate a core to Softnik on every server, so that's 4 Softnik cores. And then we just have the inefficiencies that come from incremental placement and from splitting and merging network function instances. And just in case you were wondering whether we're actually triggering migration avoidance and splitting, the number of instances over the course of the experiment varies between 22 to 56. So the instance graph is going and shrinking between 2 to 3x. I also had some other results, which I will point you to the paper on migration avoidance and pipeline-aware placement, as opposed to random placement of network functions. And in conclusion, so E2 is a runtime framework that's targeting network function virtualization or traffic processing applications. And it has a particular separation of concerns between what network function vendors are going to have to do and what the framework can do both for developers and for operators that we think can simplify both the development and the management of network functions. And with that, happy to take questions.
Mark Day. If you're doing WAN optimization in this framework, ideally you'd like to be sending a new flow to the WAN optimization module long enough for it to decide whether the flow is optimizable or not. And if it's not, you'd like to not send it to that module anymore. Is that expressible within your framework?
Definitely, because you can be updating the policy graph on the fly. That's fully intended to be dynamic.
Great, thank you.
Hi, Tim Wood from George Washington University. When I talk to networking people, they're often really concerned about the separation of the data plane and the control plane. And your work and some of my work seems to be making the data plane smarter, have more capabilities there. So what do you think about that division? And for example, it seems like you have your NFs just producing some metadata rather than explicitly taking an action about where packets go next. Is that a purposeful decision?
Okay, I missed the very last sentence. So let me start with the control versus data plane.
Sure.
And maybe you can repeat the last part of the question. I think that's a good question. I didn't go into this, which is where does this fit with the overall control architecture of a network? We think this actually fits very naturally with SDN in particular, in the sense that SDN gives you this logically centralized end-to-end way to talk about the control plane. So actually the way we imagine this playing out is that you would originally generate these pipelines from an SDN controller. This does mean extending SDN a little bit, but that's something that a lot of industry is looking into in any case. So in our view of the world, the SDN controller would hand the pipelets to the E2 controller. And it's a good division of labor because the control plane then doesn't get into the nitty-gritty of the insides of the cluster. But at the same time, it has the high-level control over what pipelines get sent to which cluster. And I don't know if that answered your...
The second part is just, do the NFs then have the ability to feed back information to the SDN controller to maybe change that pipelet topology?
In what we're currently building, the main source of feedback has to do with overload. So there's 2 forms of feedback. One is I hand a pipeline to the cluster, and the cluster just doesn't know how to run it. It doesn't have the functions, or it doesn't have the resources. So there's an error message that goes back. But the other is mostly for overload.
Great.
But it's pretty simple division.
Yeah, just a quick question. So often for fault tolerance, you would want paths that are independent, right? That don't share links, don't share switches. Would this be a framework where I could express that type of constraint, and would that be a solvable problem for you?
That's a good question. We had a paper at SIGCOMM this year on addressing how we would do fault tolerance. What we did not get into in that was how would you express the requirements of fault tolerance in your policy. We do that independent of the policy, so we know what we need for fault tolerance. You have to have an independent server, and we would do that within the framework. So it's not something that's handed down by the policy. Whether it should, I just think we don't have the experience yet to say that.
Thank you.